Welcome everyone, my name is Richárd, and now I will talk about how mostly unseen language elements can make us do subtle mistakes during development. I come from Central Europe, Hungary, more specifically from the capital city of Budapest, as we pronounce it. I'm a PhD student at Eötvös Loránd University, Faculty of Informatics, at the Department of Programming Languages and Compilers. And a short sentence summary of my research topic could be, I want to make software safer and the developer experience more rewarding. It's unfortunate that we have to meet this way. I'm sure Adelaide would have been an amazing conference experience, especially that it is my second time at SCAM. This is us in the picture together with my supervisor, Zoltán Porkoláb, back in 2017 in Shanghai. So what will I talk about today? First, I will review the environment and the necessary definitions that are needed to understand the problem. Then I will explain the basic building block of our research. And then, as this research is mostly an empirical analysis, I will detail how the analysis was set up and what we have found. Argument selection defects are the main previous research concept on which we built our hypothesis. An argument selection defect happens when the programmer, from a set of available expressions in a function call, passes the wrong argument. This is dangerous because the type system, in most cases, still accepts the wrong argument as the types still match. Such as in this example, where a string unrelated to a host name is passed as the host name, but both are of type string. A particular case of argument selection defects are argument swaps, in which the programmer passes out of order two or more arguments that were originally intended in the particular call. Previous literature has found that both the number of parameters and the adjacency of equally typed arguments, such as the two strings right next to each other in this example, increase the chance of developers making a mistake. However, previous works were mostly reactive. By this, I mean that they were built to detect call sites and compare the arguments to the parameters, for example, via their names. And if a significant difference is found, report that a swap might have happened. In contrast, our research is made from a proactive approach. By exploiting the capabilities of the type system, we can guard against swaps out of the box, making swapped expressions a hard compile error. In addition, previous works were mostly targeting Java. Let's look at an example where a function taking an integer and a complex number of the usual algebraic representation is seemingly specified with swapped arguments in the call. Will this be reported as an error by the compiler? Unfortunately, the answer is that it depends on the exact definition. We have done our research for C and C++, which languages were not investigated before from this point of view. As you can see, the complex number record type can be programmed in a way that user-defined functions can convert a complex number from and to a floating point number. In this case, the floating point converts as the real part. However, in C++, there is a language feature called implicit conversions, which makes the swapped argument call in this example compile. The results will be surprising. Let's look at the mechanism of implicit conversions through this example. We are trying to pass as argument the complex number variable c to the int parameter of the function. First, the user-defined conversion function will return a double from the complex number, its real part, and discard the imaginary part. Afterwards, due to the fundamental conversions defined in the language, every floating point number is implicitly an integer number with the decimal places discarded. Conversely, we are trying to pass an integer as a complex number. A similar conversion happens. As every integer number is also a real number, the value of 8 is converted to a double. Then, due to the existence of the converting constructor from double in complex, a complex number with 8 real and no imaginary part is constructed, and the argument is passed. Thus, the two calls seen in this example are equivalent to each other. An implicit conversion sequence from one type to another is defined in the C++ language as seen in the presentation. The sequence contains 3 elements, which are executed in order. At most, one standard conversion sequence is performed, followed by executing at most one user-defined converting function. Finally, the intermediate result might undergo at most one standard conversion sequence. The implicit conversion is only performed if there is exactly one path that can be taken. We will now show that benign-looking constructs can contain serious firepower. Now, we will look at the fundamental building block in our research, the mixable adjacent parameter range. Consider this example function in the presentation. How many of its 5 parameters are mixable? Our analysis works by inspecting the functions and calculating whether valid expressions passed to the function at a particular location might be mixed with another one. The first 2 parameters, both being the same type, are trivially mixable. An intended double, as explained earlier, can be converted between one another through a standard conversion. We have explained the path incorporating user-defined converting functions in the case of mixing int and complex. Doubles can be mixed with complex numbers purely through user-defined conversion. Finally, between complex numbers and standard strings there's, hopefully, no conversion. Thus, a mixable adjacent parameter range of length 4 is constructed, as highlighted by the squigglies. We do this for each function in the project specified. For every function, at most as many conversions might exist as there are edges in a complete graph. We have implemented the aforementioned logic in the open-source LLVM Clang C++ compiler's syntax tree-based lint tool, ClangTidy. This allowed us to use a real compiler's parser and syntax representation pre-given to us. The analysis is an opt-in feature. Due to the differences identified in the projects early on, we have implemented several relaxations of the modeling rules. These relaxations range from only considering strict type equality as mixable to allowing every implicit conversion. It is highly unlikely that existing projects can be refactored in just a few days to completely safeguard this issue. Thus, we position our investigation and implementation as a practical tool to allow enforcing a requirement of writing more type-safe code in new projects. An example output of our practical tool can be seen in this figure as visualized when ran through CodeChecker. The mixable parameter ranges are highlighted, and the tool explains the implicit conversion paths too. Let us now look at the results of our analysis. This figure details the average number of mixable parameter ranges grouped by length. It is not surprising that length 2 is the most numerous, accounting for the vast majority of cases. This is in line with findings in previous literature where reactive call-site analysis of mainly Java projects were done. The right-hand side striped columns for each group indicate the number of findings when the most relaxed, that is, all implicit conversions are modeled and considered, analysis was done. Accounting for implicit conversions changes the landscape of findings, and while it is natural that the more relaxed analysis will match longer lengths, the increase in findings surpassed our expectations. This slide shows the same plot as the previous one, but with linear scale on the y-axis. The increase of findings when implicit conversions are enabled is more emphasized in this view. However, it should be noted that not every finding increased in length, strictly. There is a corpus of new findings that are akin to a function taking one int and one double parameter. This table details the number of functions that we analyzed and how many were matched in each of the relaxations. While the exact numbers are not too important for the purposes of this talk, I have to emphasize that around 1/5 to even half of the functions contain some chance of being called with swapped arguments. Unfortunately, not every function can be refactored, even if the typesys granularity is increased ad infinitum. Functions such as min are semantically valid when called with swapped arguments, and thus no better, in some sense of the comparison, typing exists. To ensure that developers can spend their time with our results better in practice, some filterings dubbed relatedness heuristics were implemented. These are meant to filter such cases. The exact details on these rules can be found in the paper. Relatedness filtering is also a user-toggleable feature of the particular implementation. In general, we have seen that around 40% of the total findings were called by this heuristic. Now that we have seen how vast the number of findings are, the question is, who's responsible for this? After taking our measurements, we have hand-categorized every type that was involved in a report. The distribution of these culprit types can be seen in this figure, once again differentiated between C and C++ due to C having no way of automatic user-defined implicit conversions. There are two surprising takeaways here. First, when enabling implicit conversions, such as between int and double, the percentage of numeric types, such as int and double, increased greatly, and for C, almost exploded. Second, a result that might be a reason for sadness. In C++, almost half of the types of parameters in functions prone to a mix-up are user-defined, project-specific types. In these cases, the developers would have had total control over the conversions. A bit of hope stems from the fact that the percentage against the total is, at least, reasonably stable. Thank you for listening to my talk. Let's recap our contributions. We have investigated the issue of function parameters not strongly typed enough, which was previously unexplored for C++. We argued that perhaps a proactive defensive design, admittedly first for new projects, is beneficial. The data indicated that implicit conversions increase the chance of mistake, as the possibilities are extended. The effect of implicit conversions was also not discussed before, and thus a novel finding. We implemented a practical tool that is easily executable by professionals and can actively help development. A part of the paper was dedicated to discussing easy potential solutions to the type granularity issue. First, a bit of self-incrimination. Have you ever made this mistake yourself? Because I know I have. Admittedly, I've been also looking into ways to perhaps solve this problem. So the first question towards a bit more of future work. Are there any conventions you know of that people might abide to when designing their libraries? Also, what do you think? What are the first domains that we should shoot for and try to fix with regards to this type safety? Or maybe it's a general solutions that we should strive and not a domain-specific one? And my last question is, what do you think? How much hand-holding of the user is appropriate when doing a refactoring?